Okay, so the next one is exercise 35. In this one we have a finite field f whose order is 2 to the power n. We have to prove that its characteristic is equal to 2. Now here n is of course in general, when we say that a set has say 2 to the power n elements, then n is a non-negative integer. Here however, n is not allowed to be 0. That is because we do not have any field with one element. Why is that so? That's because in a field we should at least have these two elements, the 0 element and the unity, which by definition are different. So the smallest field has two elements. There is of course one such field. So n cannot be 0, n has to be a positive integer. So that means in this order we at least have at least one 2 is there. Okay. Now we want to prove that the characteristic of f is equal to 2. Since we are in a field, we know that the characteristic of f is in fact equal to the order of the unity in f considered as an element in this group, where the set is of course f, the field, and the operation is addition, the addition that we have in the field. So we start off accordingly. Since f is a field, this is the order of the unity 1 in the group f under addition. Now we know what the order of this group. This group in our case is a finite group. So we know its order. It is 2 to the power n. Since this group has order 2 to the power n, we have by one of the corollaries to Lagrange's theorem this thing. Dividing 2 to the power n. It is that corollary which tells us that if we are in a finite group, then the order of any element in the group should divide the order of the group. It's that one. Okay. Now, but we know something else about this number characteristic itself, because every field is an integral domain. So this characteristic is either 0 or a prime number, and it cannot be 0 when the field is finite. But we also know that the characteristic of f is a prime number. Okay. In this case, we have a prime number due to the finiteness of the field. In general, it is either a prime number or it is 0. So what do we get from these two things? Namely, that it should be equal to 2. There is no other choice. It has to divide 2 to the power n. So the only prime dividing a power of 2 is 2. This implies so that's how we have our solution. Let's see the next one. Determine all elements of an integral domain. Okay. Of an integral domain that are their own inverses. Under multiplication. Okay. Let D be an integral domain. Let A belonging to D be such that A is equal to A inverse. So here actually there are two things we are assuming or we are considering as our starting point, our hypothesis. One is that A is an invertible element, which otherwise is also known as a unit. That means an element in the integral domain which has a multiplicative inverse, and the other assumption is that the multiplicative inverse is A itself. Okay, then so multiplying on both sides by A we get this. Which gives us A squared minus 1 is equal to 0, or A plus 1 times A minus 1 is equal to 0. Note carefully that A square minus 1 is equal to A plus 1 times A minus 1. In this factorization, or in fact in multiplying the things out that you see here and getting A square minus 1, in general it depends on the fact that an integral domain is commutative. That means in this case, of course, since we have 1 though, we need not really care about commutativity, but I am saying in general. So what I am trying to say is this. Say you have A plus B whole square in a general ring, okay, where A and B are elements of a general ring, which may be commutative, may not be commutative, we don't really know. Say we don't know, then by definition A plus B whole square simply just means this. Now if you use your distributive laws, say you use the left distributive law first, you can then write this product as a plus b times a plus b times b, and then you use the right distributive law. You then have a times a, which of course you can write as a square, plus b times a, ba. Here also you use the right distributive law, you get ab plus b square. But unless you know that your ring is commutative, you cannot write 2ab here, because ab and ba may be different. Say you are in a matrix ring, there the calculation comes and stops here. Okay, up to this stage everything is okay, but after that you may not be able to write 2ab. But if you are in a commutative ring, you can just do your usual calculation. That's what I am saying here. When you multiply such things in a commutative ring, you don't have to worry about anything. It just goes like how we are used to this kind of calculations. But anyway, we now have this, and now of course, since we are in an integral domain and the product is 0, at least one of them should be 0. Since D is an integral domain and hence is devoid of zero divisors, a plus 1 is 0 or a minus 1 is 0, or of course both are 0. This or is inclusive or, it's understood, i.e. a is minus 1 or a is plus 1. So that means our hypothesis that a is one such element in the integral domain has led us to this conclusion that a should be minus 1 or a should be plus 1, and in fact these elements in the domain are actually their own inverses under multiplication. Since 1 inverse is 1 and minus 1 inverse is minus 1, we conclude that the only elements in D which are their own inverses under multiplication are minus 1 and 1, or in other words the unity and its additive inverse. That's just it. We won't have anything else in the domain that can be its own inverse. And related to this one, there is this next one. Characterize those integral domains for which 1 is the only element of this type. One is the only element which is its own inverse, that is its own multiplicative inverse. So let's see what this turns out to be. Let D be an integral domain where this happens. Okay, or okay, because we have to characterize, so let's just start by considering simply an integral domain. Then we will write our condition. Let D be an integral domain by the previous solution. By previous solution, we of course mean the solution to the previous exercise, not a solution to this one which comes before this, okay, not that. By the previous solution, -1 and 1 are the only elements in D which are their own multiplicative inverses. Okay, this is something which in general is true in D without imposing any further restrictions on D. But now if we want D to be this type, that is an integral domain in which 1 is the only element of which is its own multiplicative inverse, then definitely -1 should be equal to 1. They should be the same, because you cannot simply say that no, -1 is not an element of that type. No, that is already true. So the only way out of this situation is to have them equal. Conversely, if they are equal, then of course D has only one such element, and which is the unity. So D has only okay, no, not like this. So 1 is the only element in D which is its own multiplicative inverse if and only if -1 is equal to 1. This last equation is equivalent to 2 being equal to 0. Now this 2 being equal to 0 looks extremely, it seems like it is something wrong, but we are in a general ring, it may happen, and or rather let me write it like this: 1 plus 1 is equal to 0. So what do we see from this equation? From this equation we see that, if you are thinking of 1, the unit element in this group, the group that the integral domain is under addition, if you are thinking of 1 as an element in this group, then this equation tells us that 1 square is equal to identity. So from group theory, what can we say from this type of equation? Namely, that the order of 1 as an element in this group is either 1 or 2. That is because the order has to divide this exponent 2. And because 2 is prime, so it can either be 1 or 2. But it cannot be 1. Why? Because in any group, the only element whose order is 1 is the identity element. And in this group, the identity element is 0. And 1 is not equal to 0. That we already know. The unity in a ring is never equal to 0 by definition. So that is why the only possibility is that the order should be equal to 2. But this order we know is the characteristic of the integral domain D. Okay, so we are of course not going to say all of these things. We will just simply write, and this in turn is equivalent to this. Hence, precisely those integral domains whose characteristic equal, all of them equal to, they are the ones where we will have only the unity as the sole element, which is its own multiplicative inverse. If you are in such an integral domain, then unity is on the only such element, and conversely, if unity is the only such element in an integral domain, then its characteristic must be equal to D. 2. So this is the characterization of such integral domains, and it turns out that the characterization is in terms of its characteristic. So that's just it, that is the solution. And let's just end the things here itself. I could have solved one more, but I have to wake up early tomorrow because there is a test that we have to conduct in our school. Anyway, so tomorrow we are again going to do real analysis from Terence Tau's analysis 1. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.